Hi everybody. So in today's video, we're going to be doing lesson 7 from unit 3, which is figuring out whether we have an overestimate or underestimate when we use a tangent line to estimate a value for a function. So our learning target for today is I can determine, so that's kind of like decide, whether a tangent line value is an overestimate or an underestimate using something that we're going to call the concavity of the function at a given x value. So this is going to be kind of a follow-up to what we already learned about writing the equation of a tangent line. This is like a second part. So let's start with a little bit of a review of linear approximations. So what we learned in the previous lesson was that if we have a function, so let f of x equal x squared, we can do a couple different things. What we're going to do is write the equation of the line that is tangent at x equals 2, and then approximate the value of f of 3. So let's go ahead and try that. So my point here would be the point 2, 4, and I'm finding that by taking the x equals 2 and substituting it into the original function. My slope would be the derivative because I'm writing the equation of a tangent line. So step number 1 is find the derivative, which would be 2x. And if I plug in the number 2, I get 4 for my slope, which means I can write the equation of my tangent line. So I'm going to have y minus 4 equals 4 parentheses x minus 2. Now I'm going to use this to approximate what I get when I plug in the value 3. So for my approximation here, I'm going to go ahead and move this negative 4 to the other side to get y by itself, which means I have 4 parentheses x minus 2 plus 4, and then I can just substitute in my value. So f of 3 equals 4 times 3 minus 2 plus 4, which means I have 4 times 1 plus 4, which is 8. Now, you'll notice that I chose a number 3 here for our estimation. That's a little bit farther away from 2 than we would normally go. We would usually do like 2.1 or 2.2. The reason I chose the number 3 is that I know it's going to be very easy for us to find that exact value. As a reminder, this is an estimate. However, we know the exact value of f of 3. So if we wanted to calculate f of 3 exactly using the function, all we would have to do is plug the number 3 into our original function, which is x squared. So we would have 3 squared, which is 9. What you'll notice is that our estimated value was below or under our exact value. So in other words, this is an underestimate. So as a follow-up, our estimate for f of 3 is an underestimate. Because the 8, which is our estimate, is less than what we happen to know is the exact value, which is 9. What I also want to do, though, is show you visually on the graph how that's happening. So if this is the graph of x squared, and we go ahead and graph our tangent line, it's going to go through the point 2, 4, and have a slope of 4. So up 4 over 1, and then down 4, left 1. Now, I'm going to circle in green the exact value. So when x is 3, the exact value of the function is 9. But if we look at our tangent line, the estimated value is 8. So you can see in the orange here, that's our estimate. If you follow the tangent line, then when x is 3, it goes to the point 3, 8. Whereas our exact value is 9, because if you follow the actual curve, it goes to the point 3, 9. The question that we need to do, that we need to answer today, we need to figure out is how can we tell whether we have an under or an overestimate when finding the exact value is not always going to be very easy to do? And we're going to do that using something called the concavity of the function. So when we estimate our value, it could be too big bigger than the original value. It could be too small, smaller than the original value. And we can determine that using the concavity. The curvature of a function is called the concavity. So concavity is the math term for curvature, and it can be determined by examining the second derivative. So if you'll remember, way back on the first lesson of this unit, we talked about how each order of the derivative tells us something different about the original function. The first derivative tells us the slope of the tangent line. The second derivative tells us the concavity. If the second derivative is positive, then the function is concave up at that value. And if the second derivative is negative, then the function is concave down. So what does this look like visually? Concave up means that the graph looks like a cup. So it's curved like this. And concave down means that the graph looks like a frown. So it's curved like this. Now you'll notice that in each of these drawings, part of the drawing is going, for example, on this one, downhill, and part of it's going uphill. So this is different than slope. You can have a graph that is going downhill, have a negative slope, but it's still concave up. Or you can have a graph that has a positive slope, but it's still concave up. It's different than slope, it's the curvature. So if we were to highlight the sections on this graph where we see concave up and concave down, this graph would be concave up in this section of the graph, because you can see it kind of is shaped like a cup. And this graph would be concave down in this section of the graph, because as you can see, it's kind of shaped like a frown. And the concavity changes right here in the middle, which we are going to eventually call a point of inflection. It's a place where the concavity changes on a graph. Okay, how does this help us decide if a graph is, if our tangent line is an over or underestimate? Well, first what we need to do is practice figuring out whether we have a function that's concave up or concave down. So find the second derivative of the following functions and then determine whether the graph is concave up or concave down at the given x value. So let's start for problem number 1. F of x is equal to x cubed minus 2x at x equals negative 2. We're trying to figure out, is it concave up or concave down? Step number 1 is going to be to find the second derivative. So we need to find the second derivative of the following functions, which means take the derivative twice. So the first derivative here, f prime of x, would be 3x squared minus 2. And the second derivative here would be 6x. Then it says determine whether the graph is concave up or concave down at the given x value. So in this case, our x value is negative 2. All I'm going to do is plug that into my second derivative. So f double prime of negative 2 would be 6 times negative 2, which is negative 12. Because this is a negative number, the graph is concave down. It's negative, so less than 0. As a note, that means it would be shaped like a frown. For problem number 2, you're going to notice that this is a function that is defined implicitly. The y is not isolated. So when I find the derivative here to get the second derivative, I'm going to need to use implicit differentiation. So since I already have the first derivative, I'm just going to go ahead and find the second derivative. Now, I think it's going to be easier to do that if I distribute first. So I would have 20 minus 4y, which means I would have negative 4 times dy over dx. I'm going to go ahead and substitute my dy over dx back in. So I would have 4 parentheses 5 minus y. And I'm going to have, if I simplify a little bit, negative 16 times 5 minus y. The second step is going to be to substitute the point 3, 4. Now in this problem, we only need the y coordinate of that point, which is the 4. So d squared y over dx squared evaluated at the point 3 comma 4 would be negative 16 times 5 minus 4, which is just going to be negative 16. Since this is a negative number, I would say concave down because the second derivative evaluated at 3 comma 4 is less than 0, and again, that means it's going to look like a frown. Last but not least, let's say g of x is equal to sine of x. Again, step number 1 is going to be to find the second derivative. So the first derivative would be cosine, and the second derivative would be negative sine. Then I'm going to plug in the number pi over 2. Which means I have negative sine of pi over 2. Sine of pi over 2 is 1, so it would be negative 1, which means my function is going to be concave down. Because the second derivative at pi over 2 was less than 0, and again, that means it looks like a frown. Now, there are going to be functions, obviously, that are concave up. These are 3 examples. They all happened to be concave down, but there will be examples where it is concave up. Okay, how do we use this to figure out if our tangent line gives us an estimate that's too big or an estimate that's too small? We can determine whether our linear approximations will be over or under estimates by looking at the concavity of the function. If you imagine a function that is concave up, since our function is concave up, anywhere that you draw the tangent line, no matter which point the function is connecting to the tangent line at, it doesn't matter. The tangent lines will always be below the function. So all of our estimates here will be underestimates. Because the second derivative at whatever number we're checking is less than 0. I'm sorry, is greater than 0. It's concave up. Woo, what am I saying? Now, if you imagine in your mind a graph that is concave down, no matter where you draw your tangent lines, all of your tangent lines will always be above the actual graph. They're all over it. So all of your estimates will be overestimates because the second derivative at whatever number you check is going to be less than 0. You're going to have a function that's concave down. So the concavity, the shape, tells us whether our tangent lines will be above or below, and therefore it allows us to figure out if we have an over or an underestimate. Let's look at an example. The table below gives the values of f and its derivative f prime for selected values of x. The second derivative of f has the property such that the second derivative is greater than 0 for negative 1.5 is less than or equal to x is less than or equal to 1.5 is the estimate for f of 1.2 obtained by using the equation of the tangent line at x equals 1. An overestimate or an underestimate justify your answer. Now, this does not ask us to find the estimate. It just says, is the estimate for f of 1.2 obtained using the equation of the tangent line an over or an underestimate? In order to decide that, we need to look at the second derivative. Or, in other words, the concavity of the function. Now, this table doesn't give us any information about the second derivative. However, the original instructions do. The original instructions tell us that the second derivative of f has the property that f double prime of x is greater than 0 for all of the x values between negative 1.5 and positive 1.5. And our x value happens to be in between those two numbers. So if the second derivative is positive, that means that our function is concave up, like a cup, which means all of our tangent lines will be below the curve. Therefore, we are going to say that the estimate will be an underestimate because the second derivative of at 1.2 is greater than 0. For problem number 5, it says, let's let f of x be the square root of x, write the equation of the tangent line, and then suppose you use that equation to approximate the value of f of 1.2. Is the estimate an over or an underestimate? Justify your answer. So in this case, we need to, again, write the equation of the tangent line. That's part 1, which means we're going to need a point, and we're going to need a slope so that we can write the equation of our tangent. The point here would be the point 1, comma, if I plug that into this original function, I get 1. My slope, I'm going to find is easier to figure out the derivative if I rewrite this as x to the 1/2. So f prime of x is going to be 1/2 x to the negative 1/2. And if I just rewrite that with a square root in the denominator, it would be 1 over 2 root x, which means f prime of 1 would be 1/2. My tangent line would be y minus 1 equals 1/2 times x minus 1. Now, suppose that you use the tangent line to approximate the value of f of 1.2. So let's approximate. So I'm going to move my 1 to the other side, 1/2 times x minus 1 plus 1. If I plug in the number 1.2, I get 1/2 times 0.2, which is 0.1. So f of 1.2 would be approximately 0.1 plus 1, which is 1.1. So there's my approximation. Last but not least, is this an overestimate or is this an underestimate? So for this part, we're going to need the second derivative, which means I'm going to go back to the first derivative that I had over here, which I had already written it as a fractional exponent. It's going to make my life a little bit easier. So the second derivative would be negative 1/4 x to the negative 3/2, which if I rewrite that in a slightly simpler way, I would get negative 1 over 4 and then the square root of x cubed. Now I'm going to plug in the number 1 because that's where I drew my tangent line, which means I get negative 1/4. So my estimate, since my concavity is negative, or yes, since my concavity is negative, I'm concave down like a frown, which means all of my tangent lines are above. So I would say I have an overestimate because f double prime of 1 is less than 0. Now we can confirm that using a calculator. So if you actually find the square root of 1.2, you get 1.095. We estimated it was 1.1, which is a little bit too high. So we have an overestimate, and that again can be determined because we have a function that is concave down. All right, thank you guys so much for watching, and I'll see you soon for some practice.